So we are here. I did not push anything to the. This got to be the repository. I will share the repository in the email. Sorry, uh, in the in the WhatsApp group later on. So the last session we discussed about the basically what is called rune, how to work with rune, why in Golang rune is not a type, whether it is an integer or it is int 8, uint 8, uint 16, uint 32, whatever. You can store a character as long as the number is within the range of that particular data type. As long as it is a integer type, integer 8 to integer 64, uint or signed or unsigned. We can store the characters. So characters are never taken as the characters in Golang. I think characters are taken not only in Golang, any programming languages, but in Golang we're talking about. So characters are considered as basically numbers. Those numbers are UT of 8 characters, etc. This is what we are talking about. So when you go to the next example, okay, which I talk especially about strings, because if you understand strings, you understand many things in Golang. So there is a stub, and then I talk about variables, strings, variable strings. Let's talk about variable strings. Okay. So what generally I do is, for example, where str1 is string, where str2 equal to hello world, str3 equal to hello world. So there are three strings, three different way of creating a string. This is actually an empty string because which is a zero value. This is a string with type inference. That means actually whenever you create a string, you directly assign the string so that you assign the string automatically. This is considered as string, and this is the string but with a shorthand declaration. There are three strings: str1, str2, and str3. What I want to do here is there are three strings str1, 2, and 3. What I want to do is so there is something called nil. Nil. Go doesn't have null. Go doesn't have null. Go does not have null, but nil. The nil is very curious case. Is nil is very curious case in Go. Curious in Go. Curious type in Go. Interestingly, some people call nil is a type as well. Nil is a value as well. Nil is a type as well. So nil works very differently in Golang. Sometimes it looks like a type. Sometimes it looks like a. Sometimes it looks like a type. Sometimes it looks like a value. Nil is really very curious case in Go. So you understand the curious case of nil going forward when we keep on working on Go. Multiple things when you start doing, definitely you understand why I said nil is a curious case. But definitely nil is a curious case in Go. Okay, nil is a very curious case in Go. So there are many data types in Go. Okay, there is a string, there is any, there is general interface, and you're not any. Any is also interface, but there is interface. There are pointer types. Okay, there is a function, there is a slice, there is a map, there is a channel. We will discuss all these things. But if you take any of these types, what would happen is most of these types, except string, most of the types internally they contain pointer. Even the string contains a pointer. What does it mean is when I say str1, what str1 does is there is a structure internally which we call it as an internal structure of the string. Whenever you create a structure, there is a string header. This string header contains a pointer and the length. Okay. So not only string, all these types contain similar kind of a fashion. If you take an interface, if you take a pointer int, it itself is a pointer. Function, it contains a pointer. Slice, it contains a pointer, length and capacity. Map, it contains a pointer, and there is several things with the map. Channel, it contains a pointer, and there are several structured things with the map. All these types, they contain pointers. Okay. Except string, wherever you see pointer, except string. Okay, except string, wherever you see pointer, you can check that whether the type is nil or not, but not string. So what you can do is if there is a string, even though internal inside the string, which we call it as internal structure of the string, why it is you will understand eventually. Right now you may find it little confusing, but please keep it in your mind that eventually you will understand what I'm trying to say. Except except string, whatever you create, whatever the type that you create in Go, all this you can check whether it is a nil or not. For string, you have to check why it is whether it is a empty or not. For string, you check only whether it is empty or not. You never check it is okay, it's empty string, empty or not. You can check whether it's empty or not, but these the other types which you will discuss, you can check whether they are nil or not. Why Go uses only string empty or not? First thing, you can say that when I said that wherever there is a pointer. What is the meaning of pointer? Pointer holds, what is a pointer? Pointer holds the address. So generally address can be nil. If you know the foundations of C language, you can understand an address. Okay, an address is a address is nil. Okay, address is something that you can check whether the address is nil or not. Basically, okay, address means whether a variable which holds an address, it should contain either an address valid memory or not an address. That's all. Nothing else. It contains the address. To the address, you dereference that and then go to the value. You know, basic C and C++ kind of the foundations. The same foundations applied everywhere. You can check something has an address or not. Similarly, string also contains an address, but it is an internal structure. That means which we don't see that, but internally, whenever you create a string, what it does is it contains the pointer, which is 8 bytes. Generally, pointer size on 64-bit machine is 8 bytes. The length, which is integer, which is also 8 bytes. So, if you really look at str1, even though it doesn't contain anything, it is empty string. When you try to print the size of str1, how do you get the sizes? There is a package called unsafe dot size of str1. When you get the size of str1, when you get the size of str2, and when you get the size of str3, okay, let me put this over here. When you get the size of str2 and you get the size of str3, you see that all the string sizes are same. All of them are 16 bytes. So whenever you are talking about the size of a string, you are not talking about the content inside the string. You're not talking about the collection of bytes inside the string. You are always talking about the header size. It is like a structure. You are talking about the structure. That is the reason whatever the amount of data that the string is showing you or you assign to the string, basically the data is different than actually the size. Size always talks about the size of the header, not the size of the internal string. Size of the header is always 16 bytes because 8 bytes is the pointer and 8 bytes is the integer. Length is integer, pointer, this is a pointer. I think uint is a give. Pointer is always 8 bytes, length is always 8 bytes, which is an integer or uint. So 8 plus 8 is 16 bytes on a 64-bit machine. The same thing is 8 bytes on a 32-bit machine. Here it is 64 bits because we are running on 64-bit architecture, right? But I want to know that how many characters are there in the string, which we don't call it as a size, we call it as a length. Length of the string is a built-in function called length of str1. Length of a string, a built-in function called length, which is called length of str2. Similarly, it is length of str3. Length is different, size is different. Where do you get the length? The length you get from this particular variable. Why you get from variable? Because it's a pointer, initial address of the string, and the length until the length is there, it does the pointer arithmetic. That means it goes to each and every memory location by doing pointer arithmetic internally. We don't do that, but Go runtime does that. Whenever you're running applications of Go does that, but we don't do that. Pointer arithmetic in Go is internal feature of Go. We don't do that. And one more thing is, so the concept is when the string doesn't contain any kind of data, why Go doesn't treat it as nil? Why it treat it as empty? That is the important question. There are two reasons. Okay, because uh, so there is something called no object. We call it as a nil. Uh, and then the object that contains zero data. Actually, it is no object basically because the pointer is nil when you don't assign anything. Actually, what happened is the object contains zero data. Okay, so what happened is whenever you create nil stream, actually there is a nil stream, empty stream. There are two types of streams. Generally, it happens. One is called nil stream. The other one is called empty stream. Okay, nil stream means the object itself does not exist. In fact, the pointer is still nil. Okay, the pointer itself is still nil. Actually, the pointer doesn't contain any kind of data. The pointer itself is still nil. When you don't give any values, so what is the header of this? The header of this is ptr is nil, length is 0. Actually, ptr is nil and then length is 0. So the concept is why Go does that? So when it is nil, why doesn't it show it as a nil, but why doesn't it show it as a thing? Okay. So number one is, as far as what I understood is, Go doesn't want to complicate with strings. Okay, there is a zero value with the string. Go doesn't want to complicate with the string. Still the pointer is nil, the length is 0. Okay, but Go always take care about the length. If the length is 0, it always shows that it is 0. Okay, why it is goes, maybe Go may think that str1 is not a pointer. Okay, what it does is the internal pointer is nil. But you may ask the question, if you go to the next concept, why it doesn't do the same thing here? It is quite a tricky thing. Okay, the reason is Go don't want to. What I understand is Go doesn't want to complicate strings, because if it complicates the string, what would happen is, okay, it is the designers choose that. Basically, it is not actually something, because here it is nil, but string is not nil. You cannot go and then say that if str1 equal to nil, you can't do that. You cannot equal the nil with str1. But the same thing if you do with any, where any1 is any, I'll talk more about it. You can check whether any1 equal to nil. You can check this. Here it accepts, but here it doesn't accept. That's what I'm trying to say. It is the designer's choice. The designer choose this way that string is treated as a value type similar to integer. So what they did is instead of treating the string, if no value is given to the string, they don't want to treat it as nil or not nil. Rather, they would like to treat it as empty or not. So the zero value of the string is always empty string, not a nil string. Technically speaking, yes, the pointer is nil. But why they choose it? It is the designer's choice because they don't want actually the string to be a advanced type. They want the string to be very primitive type, like integer, like float and all. They just want to treat string like that, and then they choose that whenever they deal with a string, they would like to deal just with a empty or not like a nil or not. That is the first thing. So you may find it little difficult now, but eventually you will understand what I'm trying to explain. Okay, fine. And coming back here, the second thing is, what is this called? Coming back here, what is this called? Where it is stored? There are two things here. What is this called? This is called as a string literal. Hello world is called as string literal. When are you giving that string literal? You are assigning the string, you are assigning the string at compile time. There are a couple of things that you need to understand. One is you are assigning the string at compile time. Whenever you assign the string at compile time, whenever you assign the string at compile time means what? Whenever the compiler compiles the code, it understands that there is a value called hello world. Even though we did not discuss, I will tell you one more thing. What is, you may ask me, what is called runtime? Let us say that I give str4 equal to fmt.sprintf, that would convert everything to string, rand.int n of some value. What it is doing is it is generating a random value. We will discuss about conversions later. It is generating random value and then assigning the string to the string. Why it can be assigned to string? Because fmt.sprint is a function that is used actually to convert everything to a string. It is a formatter function. Anything that you give to fmt.sprint, a sprint line, whatever, it will convert everything to string. This is not a string literal. You need to understand the difference. Now, there is a clear difference between this and this. This is a string literal. This is not a string literal. Why? This function is executed at runtime and assign the value to the string. This is a string. You can see that this is a string. This function is executed. It is generating random number, rand.int, which is 999. Okay, 99,999. It is generated at runtime, not at compile time, converted to string and storing in the string. This is a different thing. This is a different thing. So whenever you create a string and assign the string at the compile time, it is nothing but a constant. You need to treat it like a constant, even though no one tell that it is a constant. You might have heard something called string is immutable. What is the meaning of string is immutable? Can anyone tell me what is the meaning of string is immutable? Why do you call string is immutable? We can't change, exactly. You can't change the string. When you cannot change the string, you may say that yes, I'm going to change the string. Okay, who said that I can't change the string? I go to str2 and then I give something, oh hello universe. You may say that yes, I am able to change the string. You are able to change the string but you are not able to change the original address of the string within this particular pointer. So what it does is it will recreate the string. It would so it leaves this as it is. It would recreate it as a separate string internally inside your memory. What that memory is called data segment inside the data segment. String literals, constants, and global variables are stored in data segment. We will see later on about the data segment, but I'm talking only about the string literal. So whenever you create a string literal, what would happen? It is immutable. So this is constant, not this is constant. This is constant. What does it mean? This is stored in the RO segment. RO is a read-only segment inside the data segment. Read-only segment means it is a constant. You cannot go and then change this value. Even the you cannot go and then change this value. In fact, you cannot go and change this value as well. If you assign a new value to the string, it always allocate new memory to the string. Then you may ask what would happen to this memory. It is a tricky part. This memory will always be there inside your application because it is stored in the data segment. Data segment is something like whenever you create static variables inside your program, they are all stored in the data segment. They'll never be deallocated from memory. Only stack and heap are deallocated. Variables from data segment and text segment would never be deallocated. So these are all called as string literals. All these string literals are stored in the memory called data segment. Those are all assigned at compile time, but this is assigned at runtime. So this variable may be stored in the stack or heap. In Go, we cannot say whether a variable is stored in stack memory or heap memory. In Go, it is purely depends on the Go compiler. Whether a variable has to be stored in stack memory or heap memory, it is purely depend on the compiler. It is called as a escape analysis. We cannot decide to store some variable in stack or heap memory. We cannot decide. So these are called as string literals. String literals are always number one stored in data segment. They are like constants because whenever you change the value to the string, it would reallocate the memory somewhere in the data segment if it is at the compile time. For example, if I go and give something like this, str2 equal to again this one I do, then this time it would not store in the data segment. Why? It is not happen at compile time. It happens at runtime. That clarity you need to have. So most of the programming nowadays, if the current trend of programming, you need to have the clear distinguish between as a developer, you should have the clarity on what happens at compile time. See, you should as simple as it is. Whenever you are developing some applications, just looking at the application code itself, you should be able to tell that what happens at what. You need to look at the code and you should be able to tell, okay, this happens at compile time, this happens at runtime, this is in the data segment, this is in the code segment, this is in the stack, this is in the heap, like that. Generally in Go, it is quite difficult to say between stack and heap, but other things you can always easily say. This is in the data segment. Why this is in the data segment? Because it is created at compile time because it is a string literal. This is in the stack or heap memory because this number is generated after executing the function. This number is generated after executing the function. See that this is the function after executing the function. When the function would be executed at compile time or runtime, the function is executed at runtime. So this is not going to be in the data segment. This might be in stack. Sometimes it might be in heap. As far as I could see that most probably in stack. I don't know about the how sprint treat, but as far as the rand.intent is concerned, it is always stored in the stack memory. Maybe a sprint we have to check because fmt.println also changes moves things to the heap memory. Most probably this could be in the I think it could be in the stack memory. That's what I'm assuming. Again, we don't know exactly where it stores. We never know in Go language until unless we run a concept called escape analysis. Okay, so you understand. See, string is a data structure. You need to have the deep understanding. Okay, so that is very, very important. And then the length of the string we already discussed in the first session. The length of the string. Yeah, please, please, Shiven, you want to ask some question? Okay. The length of the string is actually the collection of bytes, but not the collection of characters. I think we have seen most probably in the first session, whenever we created a string in maybe I think Chinese characters are somewhere. If we have not created, I think we can understand that. Somewhere in maybe one of the examples, I might have shown that. If you go here, okay, you might be having a string. Okay, I told that it is 8 characters. It is not 8 characters. I'm sorry, I put wrong. It is not 8 characters. So this is 6 characters. This is 6 characters. This is 7 characters, and then these are 5 characters. Okay. So 7 plus 5, 7 plus 6. I think 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 plus 6. It is so it is 12 characters. Sorry, 8 characters. I'm sorry. I'm sorry. 8 characters, but 12 bytes. Here 11 characters and 11 bytes. Why it is? It depends on character to character. Some of the ASCII code characters are, sorry, some of the Unicode characters are much more than 1 byte. They may be 2 byte, they may be 3 byte, and so on. That's the reason it works that way. So this is what about the string. So you understand the string. So if someone asks you why string is immutable, actually there are two ways of mutability. You need to think in two aspects of mutability with respect to string. Number one, string is immutable with respect to the data it is stored, which is called the pointer, the original pointer. The original pointer is always immutable. Okay, always immutable. Can't I mutate it? Yes, you can mutate it, but it is a quite complex process. It is a hacking your system. You need to hack your system and can do that. But by design, string is immutable. Immutable means you cannot change the value in the string. But the question number two is immediately someone asks, if you say that it is immutable, how can I change the value here? That means you are mutating it. One way you are telling that it is immutable, the immediately I am mutating it. That means, yes, you are mutating the string, but not the original address. It was. What happened is it doesn't touch this address. It would go and then recreate the string in some other memory. That memory pointer is assigned to the string. That is how we call it as a string is immutable. String is mutable or immutable. You can say yes, string is mutable as well as string is immutable. But what aspect you are asking? If you're asking about just mutating the string from the programmer, yes, you can mutate it. Are you asking mutability with respect to the runtime? Yes, it is immutable. That there are two answers you can give, but generally speaking, many people say the string is immutable. So now if I do that, str5 equal to str1 plus str2 plus str3 plus str4, if you concatenate this is called as string concatenation. What would happen is, okay, let us say not like this. Okay, this one. All four strings are concatenated for every iteration. You know that this is iteration. It does the whole operation would not happen in one single instance. This operation happens in multiple instances. So what happened is this might be added to this. The result is stored somewhere, and that is added to this. That is added to this, and ultimately the result is stored is here. So what happened is strings are immutable. Since strings are immutable, what would happen is for every iteration means for every plus operator, it would create another string, it store the value, that means it creates a new memory, it copies the value, it add a new value to that particular memory, and what would happen is every time it would keep on adding to the new memory, and ultimately it calculates everything, it compound everything, what do you say, it clubs everything, it joins everything, it appends everything, and then give you to str5. So it is a tricky part, that is the reason people say that don't do concatenation too much, because the more you do concatenation, the more you are putting burden on the string kind of a transferring. This is not on the stack memory. Sorry, this is not in the data segment, because this calculation will happen at runtime. This concatenation will happen at runtime. Since the concatenation happens at runtime, you don't know that, okay, at runtime, so what would happen, there is a lot of transfer, this is not going to be stored in the data segment, this is going to be stored in the stack or heap memory, but concatenation should be avoided, you know that already, you might have read. Okay, you should not concatenate strings. Okay, multiple times, maybe once or twice, it's fine, but you should not concatenate strings in a loop. You should not concatenate strings in an iterative process, in like an iteration. What would happen if you keep on concatenating, keep on allocating, keep on assigning, keep on allocating, keep on assigning? So what would happen is so many allocations happen behind the scene. In this case, like line number 37, it may happen in the stack or heap memory, but if it is a string literal, it may happen in the data segment. It is again, it's quite a difficult process. So it is pretty tricky part. It is pretty tricky part whether the concatenation happens at the compile time or runtime. It depends on the programming language to programming language. Okay, because it may see that string one and string two are string literals, it may happen at compile time itself. It's in our example, string one, string two. I think string four is going to happen at runtime. If you really look at it, string four would calculate at runtime. Since string 4 is going to happen at runtime, what would happen is it has to evaluate everything at runtime, not at compile time. You see that str1, str2, and str3 at compile time. You can see that. So it is a simple concatenation. So why can't it even use the string literal and store in the data segment? It can do, but the moment it look at string 4, it can understand that, okay, this is going to give you string 4, so whenever it is going to give string 4 which is going to be assigned at runtime, so it would defer the entire concatenation at runtime. So as far as I could see that in this particular context, everything happens at runtime, not at compile time. Okay, that is what actually happens. Any questions you have with respect to strings so far? Yeah, yeah, now I can hear you. Yeah. Mm. Yes, both things are both things happen at the runtime only. Yes, both things happen at runtime, because see, what is depending on what? A sprint is depending on rand, or rand is depending on a sprint. Sprint is, sorry, not a sprint or sprint. Sprint is depending on random. So unless random is generated, a sprint cannot convert it to string. So even though certain things can happen at compile time, it cannot do that. The reason is, unless rand happen, sprint cannot convert. Rand happen at runtime. Ultimately, sprint also happen at runtime. But if one more thing, actually, this is a pretty tricky part. One more thing, I'll tell you. It's a good question. The reason is, I do str2 equal to fmt dot sprint of hello world. This is actually again 37. Okay, you may say basically there are two things here. If you really look at line number 37, so you are the compiler design. Okay, yes, yes, you are the compile designer. Okay, I just keep it to you. You are a compile designer. You do compiler optimization. Okay, you are designing the Go compiler. You do compiler optimization. What do you do looking at this particular line? It looks pretty ridiculous. If you really look at line number 37, it looks pretty ridiculous. The reason is you have a string and you are converting again to a string. You already have a string, you are again converting the string. So generally what happened is most of the compiler optimization techniques, they look at line number 37, what they do is they remove this. The compiler remove this. The reason is compiler understand the result of both are same. So what happened is compiler would remove that. One more thing actually I tell you, one interesting thing I'll tell you. Let's say that I create a function called greet. I say print line of hello world. Nothing else I'm doing. Hello world. And then I call the function called greet. What it does, line number 39, what it does, Go would never, the compiler would never treat it greet as a function. Go would convert it as a inline function. Go would convert it as an inline function. What has this compiler look at that? After compiler look at that, what compiler understand is what are you doing? It is nothing, no logic is involved in that. It is just printing a string. To print a string, why should I even okay, one more thing. Let me print this, let me clear the error. So compiler looks at this. You see that even actually the linter is giving an error. Unnecessary use of fmt.sprint. The tool language static linter itself is giving some kind of an error. Unnecessary use of sprint, because forget about the compiler, even the tool that is assisting you itself caught it. This is unnecessary use. So definitely your compiler either if you are writing some kind of a production grade code, these kind of errors are not accepted because your production code would never be pushed to that particular repository as long as this is cleared, because your tools will catch this. They would never let you compile this application. Sorry, they would never let you push this application to your production applications. Okay, fine, you don't have any tools. Then what I do is, this is my application. What I do is I compile this application, go build, output is demo, main.go. So I got something called demo. I got demo. I got demo. Fine. What I do with this demo is I use go tool nm. Nm is what? Nm is going to give you the symbol information. Go tool nm demo grep of greet. So greet should be a function inside your application because greet is a function. Greet is a function. So it should show the function called greet. It has not shown you the greet. You see that greet is not shown. What Go thinks is the compiler would, so Go compiler has done a lot of optimizations. What the compiler thinks is what exactly you are doing. You are not written any kind of a logic. There is no input, there are no output. Okay. For that matter, internally also you are not doing anything. Okay, internally also you are doing not doing anything. Let's say. So what would happen is this would remove the function. So it what whenever you are calling here, what it does is it removes the function and it prints this particular word. It would remove the function, it print this. So the reason is Go compiler, understand this. This is an unnecessary function. Let me do it as an inline function. We call it as inline code. Inline code means some areas there is it's algorithm based. Okay. Some areas Go compiler thinks that there is no use of writing a function in some areas, so immediately it would remove it as a function. One more thing, I don't want to remove it as a function. I just want to keep it as a function only. I don't want my compiler to optimize it. Then you need to annotate it with a command go colon no inline. Go colon no inline. It's I don't think it is an annotation, but it's commenting way. You can tell many things to go by putting go colon. What you are telling is don't generate it as an inline function. Don't generate it as an inline function. What I do is I build again my application. I go back, the grid is created. You see that? This is what actually many optimizations Go does it. It's not like exactly what you are writing. Go does kind of an optimization. Certain things it would remove it as a function and execute it directly. Certain times you do like this, even the linter caught it. Sometimes what would happen, the linter would catch it, or the whatever the checker it is, it catches it and it says that it's unnecessary sprint. It is already a string. Why are you again converting it as a string? Here that is not the case because it happens at runtime and the conversion also would happen at runtime. See any function call you are making, any function call you are making. The rule of thumb is any function call you are making that would happen at runtime. So for example, a sprint is a function, right? I say go tool, I put a sprint. So this is the function. It is part of your code. There is a memory address for this function. It would be called. So how does the application knows that where the function is? Many people think that linker is only to link. Linker is only to link different parts of your application or different libraries or object files that are required in order to run your application. But actually, one of the works of the linter is assigning some memory to the functions. This is the function memory, F30. Okay, this is not the whole memory, but this is only the function memory. This is the memory. F30 is the memory. I think you can also print the address. Exactly, I don't know. FMT dot. Let me check it. Printf of percentage p comma fmt dot sprint. You see this. The linker has given some address to FMT. That's how does it knows that where to jump? See, whenever you say that FMT dot println a sprint, okay, how does your application knows that where to jump? That is what the symbol information is. How does it know is the linker, not linter, linker, the linking process, it gives some marking that whenever whoever calls fmt.sprint, forget about the real address, which is happens at the segment address, but there is an offset address, whatever the real memory is, but there is an offset address, jump to that particular offset address, 010. That is the reason whenever I try to print the address of a function, it has printed as 010. Forget about this part, but think about this part. 010. What does it mean? 010 is the actually offset address of a function, of this function, fmt.sprint. Similarly, you can also check with greet as well. See, you can also check with greet as well. Sorry, you can also check with greet as well. You can also check the address of greet. For example, I go here, and then I print sprint, and I also print greet 100. 100 is the address. Whenever you run that application, you see that it would print 100. It would print 010. What these are all? Your linker not only link that required binaries, but also it would help your runtime to go and then jump to specific address in order to execute a function. That is what the process of linker. Okay, linking is not just a process to include things. It is not only just to link certain things. Okay, there is a much more work than what actually we think with respect to the linker. Linker is much more bigger than what we think. Linker would go and then link many things inside your application. Okay, one of the things is understanding where it has to jump, which address it has to jump whenever you go and then execute a function. So how functions will jump to different addresses? Functions, where the functions are stored. Functions are stored in your stack memory, or functions have some well, whatever is created. A function, there is a stack pointer, but functions have some kind of a memory. How does it go to that particular memory? Because it is already written. You know that people say that whatever is going to happen, it is already written, right? Even in the compiler toolchain, it is already written where to jump whenever this is called. Whenever greet is called, it has to jump to some address plus 100 segment offset. Whenever you call a sprint, it has to jump to whatever 110 or something. What is it? 010, 010. It has to jump. It is already written. So exactly what you are doing by linking your application is you are telling your application whenever it runs where it has to jump in the future. Because compilation is not a future step. Compilation is the step that we do so that the linker, so that the binary is generated. I hope you understand what I said, right? Whatever your question is clarified, inshallah. Okay, that is what I, yeah. Hmm. That is the tricky part. It depends on whether they have optimized it or not. As far as I see that, I think if the Go compiler sees that all of them are literals, it would create another literal. If that is a good question actually. It is the optimization. So Go compiler, what is that? So what Vishal asked is, what if str1, str2, str3, and str4, for all the functions have the string literals? So actually, str4 doesn't contain string literal. This is not a string literal. It is going to be executed at runtime. So what if all these four strings are having string literals? They are not having any. None of the string is computed at runtime. All of them are computed at sorry. All of them are assigned at the compile time. So as far as I could see, because why I said as far as I could see is definitely we will get to know in pointers concept. I will show you. Okay, as far as I could see, a simple example I tell you. Let's say that I create a constant. I create a something called tick equal to maybe 60. Say I create another constant. It is called minute equal to tick into 60, for example. So I say another constant. You don't need these many. I say hour equal to mini into tick into mini into 60. If you say these three things, what these three things, when these three things are computed at compile time or runtime, constants are always computed at compile time. That means the basic level of arithmetic operation, the basic level of arithmetic operation on constants, okay, always happens at compile time, not at runtime. This all happens at compile time. Even though you write a quite a bit of a big. So best example is I create a constant, I create a variable. You can also create a variable over here where maybe something like some n equal to 10. Okay, some n equal to 10. And then I go, so let me give it as 24, not 10. I give it as 24. Okay. And then I give day equal to n into hour. It cannot computate. Why it cannot computate? N is the variable. Even though you assign a value 24 to n, n is always allocated at runtime, not at compile time. Okay. And then what would happen whenever you do, and one more thing, this may be happened, it may be assigned at actually the data segment. We will discuss about segments later on. Even then, this is at the RO segment. RO segment means even during the compilation itself, during building the binary itself, okay, it should have that value day inside its binary. The value called days. But what happened? N is a variable. Whenever a variable come into the picture, what happened? A constant cannot computate. It gives an error because variable is a value that is supposed to be assigned in the future time, not at compilation. During future, futurely in future it has to assign. So what happened is as long as n is also a constant, there is no problem. But the moment n is a variable, it cannot. So according to this particular thing, since if as your question is if all of them are string literals, then all of them are constants. When all of them are constants, most probably Golang would compute it at compile time, not at runtime. Okay, and that's what Go does that. Because Go has optimized lot of things. Okay, that is how it takes. So it is string literal is nothing but a constant, as simple as it is. String literal is nothing but a constant, and you already know that you cannot mutate it. When you say you cannot mutate it, what does it mean? It is in the RO segment, read only segment. RO is part of data segment. RO segment. It's read only. You cannot go and change it. It's only for the so when everything is in RO segment, definitely they are all constants, and then constants can be concatenated. Okay, at compile time. Again, okay, I am with a gut feeling of what happened with the constants. There may be little changes, but as far as I could see that it is at the compile time because the compiler optimizations happened at version to version very rapidly. They do certain things might be in a different way earlier, but they might have changed in a new version as well. But as far as I could see that the optimization how Go does that, I completely think that it is at the compile time. Okay, so I think we can close the session for today. This is what actually now we can continue the session from tomorrow morning onwards, like the same time, 7 o'clock, 7 to 8:30. We can have the session. Uh, for today, we can close it. So I hope we had gone through the pretty good understanding of strings. That's all. Any questions? Please do ask. Otherwise, I'll close the session. We'll meet back tomorrow. Yeah. Okay. Thank you.